Good evening. This is lecture 7 of topic 1 of unit 3, heat engines. This video will be covering the main ideas of chapter 3.3 to 3.5 of book 1. You should complete this reading before class. Here are your learning intentions and success criteria for the chapter. Please pause the video and attempt to complete the KS table down there on the bottom right. Alright, so having a look through here, we've got a few knowledge verbs and a skill verb here. What's the first law of thermodynamics? If we don't know what it is, it's pretty hard to explain what that is. And that'll also help that definition. We need to know what a heat engine is. If we're going to be able to apply this theory to it, we need to know, well, what is a heat engine? And we will need to know always efficiency, because this is one of the things we need to calculate as part of this. And so the skills you should ask yourself is, can you calculate efficiency? Okay, so in 1849, scientists by the name of Joule, which is why the unit is named the Joule, did some work that showed there was a connection between mechanical, what is commonly called kinetic energy in engineering, and thermal energy. And this connection, well, the connection between gravitational and kinetic energy was already established. If we think about common simple things, that if we take something higher, it falls faster. So we know that the more effort we put into lifting something higher in a gravitational field, the faster it goes, the more kinetic energy it has. And so what he did is he used a falling object to spin paddle wheels in a container of water. Oops, I don't have the diagram there. Here it is, sorry. Basically, here we have this falling weight. It pulls on this string and it spins the paddle wheel. Okay, and so he measured the temperature before and after, and he found that by doing this, there was a change in temperature. And this showed that a mechanical work, a force over a distance, here it is, force times distance is equal to work, could result in a change in temperature. Okay? And this showed that heat was a type of energy that could do work. Combustion vehicles like cars, buses, motorcycles, and if you've been driven in them, they are a thermal, that's a vehicle where thermal energy does the work. Okay, so this was Joule's big idea that heat is able to do work. Now, back in lecture 2, we discussed that the change in internal energy in this unit would be the result of change of thermal energy. But because Joule's come along and established that heat can do work, we need to consider any work done to the system or by the system as well in that actual equation. So here's what we started with: delta U equals Q. We're going to use work is W, and so we have this final formula. Change in internal energy equals the change in heat energy, the Q, plus the work. Now, this is how it will be written in your formula booklet, and we'll get to some important things about W in a second. We can model energy inputs and outputs using a square model. There's some good examples of this in your text, but to keep it simple, let's say we have something, I don't know, maybe it's me on a hot day. If we think about it, if I'm sitting here and there's a bit of sunlight, there is some heat coming in. Okay, I'm giving off heat. Okay, and I might be doing some work as well. Okay, but maybe maybe I'm being flown around. Perhaps I'm in a plane while I'm recording this, and that plane would then be doing work on me as well. Oops, there's a very stupid looking arrow. So any system can be represented as, or the energy of a system, a change of energy of a system, can be represented by considering, well, what energies are coming into it, what energies are going out of it. So what work is going into it, what heat is going into it, what work is leaving it, what heat is leaving it. Now, on these sort of models, everything has to be a positive. Okay? We're not dealing with negatives here, but we want to find the differences. The net value for work or heat is done by taking the difference. Work in, take away work out. So here's work in, here's my arrow, take away work out. If I was not having any work done to me, then obviously my work would be some negative number because I'm losing energy. Same thing for Q in versus Q out. It's like a bank balance. Now, this formula, this is basically the first law of thermodynamics. We taught to you as the conservation of energy back in grade 8. The total energy, remember, of an isolated system is constant. We can't transform, we can transform energy, but we can't create it or destroy it. Now, the really annoying bit is sometimes texts will write the formula like this, where change of internal energy is Q take W, and they use the idea of work being done by the system. They're trying to work out, well, what's the net amount of work being taken out of the system, and that's how they define their positive. So some work might be put in, but if some work is being taken out, there's their thing. While we're looking at in terms of W being the work done to the system. Unfortunately, there's not really an always convention for it, but the good news is a little bit of common sense will help you think about what your final result should be, in that should W end up being negative because energy is being taken out of the system, or is W going to end up being positive because energy is flowing into the system by something else. If I was to go with, where's my, let's take a computer for example. My internal energy would be my change in heat, but let's say that some energy is coming out, for example, to run my video camera that's recording this, or to run the headphones that are recording the sound. Well, that energy we could represent as some positive number that is being subtracted from it. But if I was then putting work into it, maybe an old joke about bad computer services is a hamster in a wheel running around to power the computers. And if you've ever had a really bad video game online, perhaps that's the case. Well, that minus work would be the work out, but then we would have to add the work in from our little hamster buddy. Now, if we define work out as being the positive, then this will end up being subtraction of some big number. If we define work in as being the positive, well, I'll represent it like this. If we go work in equals plus 50, but work out equals minus 100, well, the result would be minus 50. And that would work under our first formula, the Q plus W, but W here is equal to minus 50. But if I define work going out as positive, work out equals 100, work in equals negative 50, so the result would be 50. But here we can see it's going to be minus our positive number here, minus our 50. Okay, and so it doesn't matter which you use, it just depends on what you define as being the positive thing. If you define work leaving an object as being the positive, like some texts do, you have to do it like this. If you define work into the system as being positive, then we define it like this. I kind of like this idea because what they're saying then is all ins are positive and all outs are negative. Yeah, you're being consistent with it. You don't have to worry about, well, is this being done to, or is this being done by? Is it work? Is it heat? It's just, it's going into the system, it's being done to the system, it's positive. Being done by the system, it's leaving the system, it's negative. It can make it a bit easier. So, let's have a look at some examples. So here's a table that's very blurry, I do apologise. This is table 3.4a on page 121 in your text, and you're given here a table of Q, W, UI, UF, and change of U. So we have our Q equals, oops, where's my thing? So we have our Q equals unknown, W equals 6, our UI equals unknown, our UF equals 35, and our change in U is equal to 24. Alright, well, if our change in U is equal to 24, and let's start with our really simple definition of what change means in this case. So change, remember, equals U final take away U initial. That's what a change always means. Final take away initial. So if I start with, or if I end at 35, and I had a change of 24, that must mean UI is equal to 11. I'm sure you can rearrange that. But if we want to look at, well, what's the individual components of it, remember that by our formula, delta U equals Q plus W. We're given W, the work is 6, the change was equal to 24, and we don't know the Q. Well, we can see from, again, simple rearrangement, Q will equal 18 joules of energy. Moving on to our next example. Now this is same sort of idea, but instead of information being given to you in a table, it's given to you in a story, which is a lot more common. So we have here a foam cup is filled with hot water and allowed to cool while being stirred by a paddle wheel. So basically it's like Joule's experiment, but we've got a hot water that's cooling down. Initially, the water has an internal energy of 200 kilojoules, and while cooling, it loses 150 kilojoules. But the paddle wheel does 25 kilojoules of work on the water. That word on, that's a really important word there, because it's telling us what direction the work is going. Calculate the change in internal energy of the water, calculate the final internal energy of the water. So let's draw our box. Here's our water. It's a box. We have our Q in. Okay. Now let's have a look. Initially, there's an internal energy of 200 kilojoules, so we have to give it some amount of energy in, but there's nothing else here saying how much energy is going into the system. Here, our Q out, it says it loses 150 kilojoules of heat. 150 kilojoules. But the paddle wheel does some work in. So our work in is 25 kilojoules. So let's have a look. Our net Q, okay, so output take away input. So Q out take away Q in. Well, here's our output, 150. Okay, and here's our, what's the word I'm looking for? Our input, which is 0 in this case. There's nothing there that's being given to us. Sorry, input take away output. I've got that around the wrong way. Let me just drop those out. Eraser. Sorry, Q in take away Q out, and so yeah, nothing's coming into it. Take away the 150 gives us negative 150 joules. I mean, that makes sense. It's losing energy. It's cooling down. It should be a negative. Sorry, kilojoules, not joules. But our Q net, work net equals Q. Whoops, W, not Q. W in take W out. Well, we put 25 in, but we didn't add any more. We didn't use it for anything. So 25 kilojoules came in. So if we think about our formula there, our change in internal energy equals our Q plus our W. Well, our Q we just worked out as being negative 150, and our W is 25. So that means the change in internal energy was 125 kilojoules. Okay. Now, the last thing it's asked, well, what's the final? Well, to the final means we need to know what we start with, and what do we take away, what do we add to it. So, our initial, according to the question, was 200 kilojoules. We just worked out our change, so a couple of ways you could write it. Change equals final take initial, or you can go, well, final equals initial plus change, because that's what it is. You start somewhere and you add your difference. The initial was 200, and we're going to add negative 125 equals 75 kilojoules. So let's ask if that seems reasonable to ourselves. We have some water with some amount of energy. It loses a lot of energy cooling down, but we do keep stirring it for a little bit to try to keep it warmer a little bit longer. So it loses a lot of energy, but gained a little bit back. Our final number is less than what we started with, so it pretty much makes sense. Okay, next word example. A pump full of compressed gas is allowed to expand, and 80 kilojoules of work is done by the gas. By the gas, that's important. On some object in the lab. At the same time, the gas is warmed by the addition of 100 joules of heat. Okay? If the initial energy is 500, calculate the final. So to work out the final, we need to know what the change is. Once we know what the change is, then we can work out, well, what the result will be. So again, let's draw our system. I'm going to use a circle because it does say it's a pump. I'm thinking like a balloon, but let's see. So Q going in. Let's see. Gas is warmed by addition of 100 joules. So Q in equals 100. Work in equals 0. Work out, we're told that it does 80 kilojoules. That's a lot of... Oh, that's interesting. Just note here, it says 100 joules, but the worked example uses kilojoules. Now we're going to use kilojoules because if you're only adding 100 joules but you're taking out 80 kilojoules, adding 100 doesn't mean anything really, simply because 100 joules compared to 80,000 joules, well, who cares? It's basically like if you've got $80,000 in your pocket and a $100 bill falls out, you're probably not going to notice it too quickly. So work going out was equal to 80, or 80 kilojoules, and Q out equals 0. There was no Q leaving. So our Q, I'm just going to write Q, not Q net. Incoming 100, take away 0, equals plus 100 kilojoules. Our work, incoming was 0, take away 80, equals negative 80 kilojoules. Now change in energy is Q plus W equals 100 plus negative 80 equals 20 kilojoules. And we want to know our final, and our final is equal to initial plus the change of U. And our initial, according to the question, was equal to, where was it, 500 kilojoules. Plus what we just worked out, 20 equals 520 kilojoules. Okay, I will double check that Walding has fixed up the errata for that one, but he probably has because this was mostly looked at last year by the other students. So that's looking at the total change of internal energy. Now what I'd like to do is do a bit of a practice. I would like you to do an energy model for an object or two around your house, just looking exactly like this one from the textbook. Your phone, your computer, TV, kettle, toaster, anything simple around the house for electricity. These are nice and easy for you to do because a lot of them will have heat coming off of it. You might think about heat coming into it and thinking about the work being done by the system as well. So go have a go with that, and I'll meet you back here in a second. Okay, so if we think back to when we were talking about energy transfer around video 3, heat moves of its own accord from areas of high temperature to areas of low temperature. Okay, that's nothing particularly new. Ice cream melts, heat moves into it. Hot drinks cool down as heat moves out of it into the environment. Your computer that you might be watching on this has fans. There's a moth trying to learn physics to help move heat in the hot air away from the computer faster. Your front of cars have vents to help cooler air come in under the bonnet to keep the engine temperature down. And so if energy is moving between places, it can be harnessed to do work. And this is what we call a heat engine. You can see at the top here we have a heat reservoir where things are hot, Down here is a cold reservoir, otherwise known as a heat sink. And so, oops, let's get him out of the way. Yeah, go away. Apologies for that. And so we can see here energy will move from high point to low point, but we can steal a bit to do some work. Okay, so this is called a heat engine. Any combustion process that we use to do something can be considered a heat engine. The heated gases or heated liquid does some work, and in the process they will get colder. An air conditioner that makes the room colder is the opposite. It's called a heat pump. We take energy from the cold environment and put it in a warmer environment, and so we need to give it some energy to make this go the other way. So if we want to make this arrow go from here to here, we need to add some energy in through that way, which is why your air conditioning unit always has a bit of heat being produced. Or you might often see it with condensation, because there's some funky stuff going on there. Now, as you may have saw just a second ago with our little moth friend, if we take this total energy flowing into the system and the work produced by the system, the ratio will give us what we call the efficiency. And it just looks like this. We take the output, and we divide it by the input, we get efficiency. Now, the one in the the formula booklet says output over input times 100%. I'm happy to just do output over input, but remember, if a question on your final exam asks for it as a percentage, you have to give it as that percentage. If your answer was 0.33 and you wrote 0.33, they may mark it wrong, especially if they asked for a percent, because it wouldn't be 0.33%, the answer would be 33%. So just be aware of that and think about what's going on with it. So let's have a look at some examples of this. This one's pretty straightforward. Here we have a thermal energy transfer. This is work example 3.5. We have a heat engine here, and we can see at the top, the Q of the hot is 60 joules, so 60 joules of heat energy is coming in, and 10 joules of heat energy is coming out down the bottom at the cold reservoir part. But there's some work leaving out the system here off to the side. And so our first question on here is, well, how much work is actually leaving the system? So what we can think about here is that if we have that the change of energy, okay, because the change of energy for this whole system has to equal 0. Okay? What we get in from our heat, what leaves as our heat, the difference has to be equal to our work. So the change of internal energy has to be 0, because we're not adding extra to this system, we're just harnessing its movement. So if we write that in there, 0 equals Q plus W, then by extension we can say, well, our change in work is equal to our Q, or we can go the other way with negative Q equals positive W. But let's think about our Q there. So our Q is input take output. Well, our input equals 60, and our output equals 10. So our Q must equal 50. Okay, there has to be a change of 50 there. Well, that means our work must equal negative 50. And if we think about this, well, if I start with 60 and I have 10, that must be equal to 50 joules leaving the system. Okay, now that's what that negative here implies. The negative means the energy is leaving the system. It's negative 50 joules. Remember, you can't have negative energy, but because it's a scalar quantity. However, sometimes negative energy tells you about, is this energy entering a system or is it leaving a system? So the negative sometimes can be useful. Now, if you're dealing with a heat engine, the work out should be negative compared to the energy flow. Okay? Unless we have that we're being told energy starts here and goes up to here, in which case then if the arrows are all reversed, we had to give 50 joules of energy to make the thing heat up. So hopefully that bit there wasn't too difficult. Now the next part here is asking, well, what is the thermal efficiency? What is the efficiency? And as we just saw, our efficiency formula, eta, I know it looks like an N, but it's the letter eta, is output over input. Well, output was 50. I'm going to just use the absolute value. We don't need to worry about the negative. because a negative percentage doesn't make sense. And the input, well, the input's up here, 50 over 60 equals about 0.833, so that's about 83%. Okay, not a bad efficiency. In car engine is 20% according to the text. I think I overestimated a little bit today. So these things are not, super effective heat engines. Really good bit if you read the text. The steam engines are only about 8%. So heat engines aren't amazing. Now this is the only example for this because it's a very simple idea. Input divided by output, we've got output divided by input, we've got our efficiency. Okay, so in this video we've done the following. We've explained that heat energy has a capacity to do work. We've defined change of internal energy and efficiency of engines, and then we've calculated these two things as well. Now for your entrance slip to class, there are a few questions associated with this. Questions 1 to 4 in chapter 3.4 and questions 1 to 5 in chapters 3.5. Please copy your answers into 3.1.7 on eLearn. Thanks very much for listening. Have a great night.